Have you ever really stopped to think about what's happening deep inside your computer? I mean, at the most basic, fundamental level. It's not really about complicated math. It's actually a surprisingly simple and incredibly powerful language of pure logic. And in this explainer, we're going to pull back the curtain and look at the basic instructions a processor uses to handle data one tiny bit at a time. So here's what we've got on tap. We'll start with the computer's three main tools for working with data. Then we'll dive right into the world of zeros and ones to really see why they're so important. After that, we'll get into the core logic toolkit itself, see it in action with some pretty cool real-world examples. And finally, we'll find out how just a single bit can control the entire processor. Okay, so when a computer's processor needs to get some work done with data, it doesn't just have one way of doing things. No, it has a whole toolkit, and each tool is designed for a very specific job. Now, this toolkit is pretty much split into three main categories. You've got your arithmetic instructions. That's for all the math stuff, adding, subtracting. Then you have shift instructions, which are for sliding bits left and right. But today, we are zeroing in on that third, and you could argue the most fundamental category, logical instructions. These are the tools a computer uses to make decisions one bit at a time. That's a fair question, though. I mean, if we already have tools for doing math, why do we need this whole separate set of tools just for logic? Well, the answer gets right to the heart of how a computer actually thinks. And the answer is bits. It's that simple. Absolutely everything a computer does, from playing a movie to sending a quick text, it all boils down to billions and billions of tiny little on or off switches. And we represent those with zeros and ones. Logical instructions are a way of reaching in and directly controlling those fundamental little building blocks of our digital world. And this is exactly why these logical instructions are so darn powerful. Look, arithmetic is great for the big picture, like adding up a column of numbers. But what if you need to do something super precise, like flip just the third bit in a byte from a 1 to a 0 without touching anything else? Well, that's where logic shines. It gives programmers, especially the ones working in low-level languages like C or assembly, the kind of precision you'd expect from a surgeon's scalpel, letting them manipulate individual bits to control very specific features. All right, let's crack open this logical toolkit and see what's actually inside. We're about to meet the four absolute workhorses of computer logic: AND, OR, NOT, and XOR. If you can understand these four, you've basically unlocked the secret language of digital computation. First up, we've got the AND operation. The rule here couldn't be simpler. The output is 1 only if both of the inputs are 1. If even one of those inputs is a 0, the output is 0. A really easy way to remember this is to just think of it like multiplication. Anything times 0 is 0. Same idea. And this truth table here shows you exactly how strict the AND operation is. You can see it right there. The only way you're getting a 1 on the other side is if input A and input B are both 1. Every single other combination gives you a 0. Okay, so because of this very strict rule, we can do something really clever and powerful. Since we know for a fact that anything ANDed with a 0 becomes a 0, we can use this to precisely clear out or erase specific bits we don't want. We do this with something called a mask. Just imagine the mask is like a stencil you'd use for painting. We build this mask with zeros in the exact spots we want to clear. Then, when we apply that mask using the AND operation, any bit that lines up with a 0 gets forced to become a 0, while any bit that lines up with a 1 gets to stay exactly as it was. It's a surgical tool for data. Next in the toolbox is the OR operation. Now, if AND is the super strict bouncer at the club, OR is the friendly host welcoming everyone in. The rule for OR is that the output is 1 if at least one of the inputs is a 1. For this one, you can kind of think of it like binary addition. If you add a 1 to anything, the result is going to be 1. And you can see that welcoming nature right here in the truth table for OR. The only time we ever get a 0 as the output is when both inputs are 0. Any other time, if there's even just one 1 in the mix, you're guaranteed to get a 1 as the result. So let's just put these two powerful tools side by side for a second. AND is what we use for a selective clear. We use a 0 to force a bit to turn off. OR is for a selective set. We use a 1 to force a bit to turn on. They're like the yin and yang of bit manipulation, and together they give us total control over our data. Now for the simplest tool in the entire kit, the NOT operation. It's also called the complement. This one's a bit of a rebel. It does exactly what it sounds like. It just flips every single bit. All the ones become zeros, and all the zeros become ones. That's it. Dead simple. And finally, we have XOR, which stands for exclusive OR. And this one is our difference detector. The output is 1 times only if the two inputs are different from each other. If they're the same, so 2 zeros or 2 ones, the output is 0. It's all about being exclusive. And here's a nifty little programmer's trick for you. You can actually pull off a NOT operation just by using XOR. If you take any string of bits and you XOR it with a string of all ones, you get the exact same result as a NOT operation. It flips every single bit. It's just a really clever example of how these simple little rules can be combined in some pretty surprising ways. Okay, so we've gone through all the theory, but where does this stuff actually show up in the real world? I mean, it's not just abstract, right? Let's take a look at a couple of examples where these logical tools are working away silently behind the scenes in things we use every single day. Let's talk about the internet. Every single time your computer sends out a packet of data, routers all over the world have to figure out which network it belongs to. How do they do that? You guessed it, with a simple AND operation. They take your computer's IP address and they AND it with something called a subnet mask. And boom, it instantly calculates the network ID. This tiny little logical step happens billions of times a second, all over the planet, and it's what makes the entire internet work. Here's another beautiful example of just how elegant this can be. How does a computer figure out if a number is even or odd? Well, it turns out that in binary, every odd number ends with a 1. So all you have to do is take your number and AND it with the number 1. If the result is 1, you know the number is odd. If the result is 0, it's even. It's an incredibly simple, fast, and efficient check that's built on the basic logic we just covered. Okay, for our last section, let's zoom out a little bit. We've seen how these logical operations can change data, but they can also be used to control the processor itself. They act like tiny little on-off switches for some of the chip's most critical functions. And this is often done using something called an interrupt. The best way to think about an interrupt is like a tap on the shoulder for the CPU. It's a signal that basically says, hey, stop what you're doing for a second and pay attention to me right now. This happens every time you press a key on your keyboard, every time you move your mouse, or every time a little bit of data comes in from the internet. It's the secret to how your computer can seem to do so many things at once. So how does the CPU manage all these potential interruptions? Well, it uses a single bit, often called an interrupt flag. When that flag bit is set to 1, which it does using a logical OR operation, the CPU is basically in listening mode, ready to respond to any of those taps on the shoulder. But when it's in the middle of a supercritical task that absolutely cannot be disturbed, the CPU can clear that bit to 0 using a logical AND operation, which is like putting up a big do not disturb sign. The entire ability for the computer to focus is controlled by one tiny bit. You know, it's pretty amazing when you just step back and think about it. These incredibly simple rules, AND, OR, NOT, and XOR, they are the bedrock for almost everything in our modern world of technology. From the most basic calculation to the unbelievably complex symphony that is the internet, it all comes back to this simple, elegant language of logic. It really makes you wonder, doesn't it? What other complex, beautiful systems in our universe are actually built on just a handful of simple, elegant rules?